Lesson 2-6, Zeros of Polynomial Functions. We have come to the fundamental theorem of algebra. It says if f of x is a polynomial function of degree n, then there is at least one zero. So in other words, if you have a polynomial function and it equals 0, you can solve it. Corollary to it says there's exactly n zeros. So whatever the degree is, that is the number of zeros. And there are exactly the same number of linear factors as degree. So if the degree is 5, there are 5 zeros and 5 linear factors. Alright, so let's find all the zeros for this. It's x to the 4th, so we'd expect 4 zeros. Now, the way students want to do this is add the 16, and then you'll take the 4th root. Since it's an even root, you'll go plus and minus, and so you'll get plus and minus 2. So you'll get 2 and negative 2. Except for that's only 2 zeros, and we need 4 of them. So let's try again. Let's try by factoring. This is the same thing as x squared squared minus 4 squared. So this is a difference of squares. So it's a squared minus b squared is a minus b, a plus b. Oh, this first one is also a difference of squares. So it'll be x minus 2, x plus 2. The second one is a plus, so that is not factorable. So now I've factored it. Then we take each factor equal to 0. So okay, x is 2, x is negative 2, x squared is negative 4, and then we need to square root that. When we square root it, don't forget the plus and minus. Let's see, the square root of a negative 4 is 2i. So our answers are negative 2, 2, negative 2i, and 2i. So there we go, 4 zeros. 2 of them happen to be imaginary. Let's find all the zeros of this polynomial function. We don't know any of the original factors or anything, so what we're going to do is we're going to do the p's and the q's. Since I can't factor this very easily. Get 30 is 1 times 30, or 2 times 15, or 3 times 10, or 5 times 6. Quite the list. Q's. Q's are factors of the leading coefficients, which is 2. So that's 1 times 2. So P's over Q's are all the P's divided by all the Q's. So we could have 1 over 1, 1 over 2, 2 over 1, or 2 over 2, which is 1. I already have that. Or 3 over 1, or 3 over 2. 5 over 1, or 5 over 2. 6 over 1, or 6 over 2, which is 3. I already have the 3. 10 over 1, or 10 over 2, which is 5. I already have that. 15 over 1, 15 over 2, 30 over 1, or 30 over 2, which is 15, and I already have that. So we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24 numbers to choose from. You may think that's quite a long list, except for it's much shorter than an infinite number of numbers before we made the list. But it would be nice if we could narrow this down. Remember, since we have technology, that the zeros, the real zeros, are x-intercepts. So if we look at our graph, it looks something like that. And we have a number right here. That is a 2. One x-intercept is a 2. So we could start by trying 2. Do synthetic division. 2x to the fourth, negative 9x cubed, negative 18x squared, 71x, and negative 30. Bring down the 2 and multiply. Add. Multiply. Add. Multiply. Add. Multiply. Add. Look at that, we got a 0, so 2 is a 0. And now we have a depressed polynomial of 2. It was x to the fourth. We're depressed, we lost a power, so it's x cubed. Minus 5x squared minus 28x plus 15. All right, that is still cubic. I can't factor that very easily. So let's use that with synthetic division. So if I look at our graph again, here's another x-intercept at a 5. So let's try that one. Let's use the depressed polynomial though, not the original, the depressed, because all the zeros or all the factors of the original are in the depressed except for the first one we divided out. And we're not using that 2 anymore, so this will help us. Bring down the 2 and multiply, and add, and multiply, and add, and multiply, and add. Oh, look at that, we got another 0. The 5 is another 0. Okay, that was x cubed, so now our depressed polynomial is x squared, plus 5x minus 3. So now we're at a quadratic. We can factor quadratics really easily. And that is the purpose of using the depressed polynomials. You divide, use the depressed polynomial. Divide, use the depressed polynomial. Until the depressed polynomial is a quadratic, which you can just solve by factoring or the quadratic formula. To get 2x squared is 2x and x. To get negative 3 would be negative 1 plus 3. We check, that is 6x plus a negative 1x is 5x. That's our middle, so it works. So then we take each factor equal to 0. We get x is 1/2 and x is negative 3. So notice we have the 5, we have the 1/2, and the negative 3. They're all in our list. So it's negative 3, 1/2, 2, 5. It was x to the fourth. Our degree was 4. We got 4 zeros. Now, what if we didn't have the graphing calculator to find our x-intercepts to make our choosing our numbers from the list of possible rational zeros quick and easy? Well, Descartes came up with a way to narrow the list down further using the rule of signs. It says if we have this function, real coefficients and a0 isn't 0, then the number of positive real zeros is equal to the number of variations and signs of the function, or less by an even integer. So you're going to go along, you look and see how many times the signs between the terms change. The number of positive zeros equals to the number of times the sign changes, or less by an even integer. So if there was 5 changes, it'd be 5, or 3, or 1. If there's 2 changes, it'd be 2, or 0. Just count down by 2s until you hit 1 or 0. The number of negative real zeros is equal to the number of variations and signs in f of negative x, or less by an even integer. So to find the number of negative real zeros, you have to plug in a negative x and then do the same thing you did before. And so this will tell you, say, oh, there's no negative zeros. Great, let's not look for any. Well, there's no positive zeros. Great, let's not look for any. Well, there's only one, but there might be 2 or 0 of the other. So it helps you decide which numbers to choose from. All right, let's describe the possible real zeros of this function. As in how many positive, how many negative. So let's start with the positive. So, and the positive, we just look for the number of variations in signs. That goes from negative to positive. So there's 1. Positive to negative is 2. And negative to positive is 3. So there are 3 positive real zeros, or less by an even number. So if we subtract 2, we'd get 1. So 3 or 1. And we subtract 2 zeros because there might be imaginary zeros, which always come in pairs. Like when we solve them with the quadratic formula, you always get the plus and minus. So it's 3 or 1. You count down by 2s. For the negative, we have to find f of negative x. So we're going to replace x with negative x and simplify. So negative x cubed would be negative x cubed times the negative 2 would become positive 2x cubed. Negative x squared is positive x squared, so it's still positive 5x squared. Negative and negative is a positive. And we look at how many times the sign changes here. Well, they're all positive. They're all positive. So there are 0 negative zeros, because there are no variations in sign. So, if you had your long list of the p's over the q's, you have the plus and minus 1, plus and minus 2, plus and minus 5, plus and minus whatever. We have just looked at this one and said, oh, there's no negatives, so don't look for any. We just cut our list in half. As we're talking about the types of zeros we get, I said that we subtracted or we counted down by even numbers because the complex numbers always come in pairs, which is the complex conjugate theorem. If a complex number a plus bi is a 0, then a minus bi is also a 0. It's always a plus and minus bi. So let's use that idea to go the other direction. Find a polynomial function with real coefficients and these zeros. So if those are zeros, the factors would be x minus each of those zeros. So x minus a negative 1, x minus 3 plus square root of 2i. Oh, but wait, if we have one complex 0, then its conjugate is also a 0. X minus 3 minus square root of 2i. All right, since we just want a polynomial function and not a specific, we want any polynomial function with these coefficients, with real coefficients and these zeros, instead of having this fraction, what if I were to multiply both of those by 3 to make it 3x minus 2? So times by 3 times by 3. Does that give me the same 0? Sure, if I made that equal to 0, I'd add the 2 and divide by 3 and get the 0 of 2/3. Right? 3x minus 2. So we just went backwards. So think of starting with x equals 2/3, multiplying by 3, subtracting 2, and that's our factor. Let's distribute the negatives. And then multiply together. Let's do this in 2 steps. Let's multiply the first 2 together. So 3x times x, 3x times 1, negative 2 times x, negative 2 times 1. Let's do the second group. X times x times negative 3, x times square root of 2i. Negative 3 times x, negative 3 times negative 3, and negative 3 times the square root of 2i. Negative x times the square root of 2i plus 3 square root of 2i, and minus square root of 2 times square root of 2 is 2. Then we have I squared, which is negative 1. So that becomes plus 2. Combine like terms. This will become x. We have negative 3x and negative 3x. X squared root of 2i minus x squared root of 2i cancels out. Negative 3 squared root of 2i and positive 3 squared root of 2i cancels out. So then I have 9 and 2 is 11. Now multiply these. 3x squared times x squared. 3x squared times negative 6x. 3x squared times 11. X times x squared. X times negative 6x. And x times 11. Negative 2 times x squared. Negative 2 times negative 6x. And negative 2 times 11. Collect like terms. Cubes, I have 1x cubed. That should have been a cubed. So I have negative 18x cubed, and 1x cubed is negative 17x cubed. For squareds, I have 33. Minus 6 is like 27. Minus 2 is 25. Just x's, I have 11, and 12 is 23. And the minus 22 at the end.